Here are all the circuit symbols, okay? Don't get them confused. LDR, it's not an LDR. Look at the difference between an LDR. So LDR is, oh, let me close this. LDR has got a resistor with arrows going inwards. LED has arrows going outwards. This one has arrows going outwards. It's a diode because it's got that little triangle inside. Whereas an LDR has a rectangle inside. So the answer is actually LED, not LDR. So this here is an LDR, rectangle in the middle. LED is the one with the triangle in the middle. Next question. When the switch was closed, the current in component X was something. The current in the resistor. What do you guys think? This is all about series and parallel circuits. Is this a series or parallel circuit? What's the difference between the two? Series means it's all in one loop. Series means it's in one loop. Parallel means it's in multiple loops. This is all in one loop. You can see all of this is in one loop. So this is a series circuit. This question is asking about current. Current in a series circuit, if you look at the notes, is the same through each component. So the answer is the same as. The same as the current in the resistor. Okay, so this question is all about, it says a designer made some shoes that have lights in them. Each shoe has a switch which closes when a person puts their foot on the floor. So basically, imagine a shoe. At the bottom, you have this circuit, and every time you step on the floor, that pressure is going to cause this switch to close. So when that switch closes, it's going to cause this LED to light up. So it's one of those shoes that light up when you walk. Okay, and the next bit is saying the designer tested how the number of cells, remember cells are just like batteries, for example, affected the number of steps that could be taken before the light stopped working. So obviously, if you have anything that's battery powered, after a while, you're going to run out of battery. You're going to run out of chemical energy from the battery. So the more batteries you have, the number of cells, the longer you can keep lighting up the lights on the shoe. So that's why it keeps going up. Determine how many more steps could be taken when the number of cells was increased from 3 to 5. So 3, look carefully where the 3 is. So the 3 is halfway there. And then 5 is the one, it's the very last one. That's also halfway. So look at those two numbers carefully. It's right in the middle. So this one here, I would say is 900. This one here is 1,500. How many more steps could be taken? You just need to subtract the two. So 1,500 minus 900, which gives an answer of 600,000. Yep, well done, guys. How could the designer check the repeatability of the results? Repeatability. Okay, so just remember what that means. Repeatability is when you do an experiment and you do it again and you try and get the same outcome. So you keep doing the experiment again using exactly the same method and you expect the exact same answers as well. So that's what repeatability. That's how to test repeatability. When the potential difference across the resistor was 0.5 volts, the current in the resistor was 0.02 amps. Calculate the power dissipated by the resistor. They've been nice here. They've given you the equation. Potential difference times by current. So all you need to do is 0.8 times 0.02. If you do that, you get, careful with your numbers, careful with your zeros. When you put that in the calculator, remember that there should be an extra zero in there. So it's 0.016. Don't write 0.16 watts. Which other equation can be used to calculate the power dissipated by the resistor? So you get given equations this year. So this should be really easy. You just look it up in the equation sheet. P is equal to I squared R. So it's going to be the top one there. On to the next one. What happens to the temperature of the resistor when there is a current in it? What happens to the temperature of the resistor when there's a current in it? So whenever current flows through like a wire or any component, like a resistor, wire or resistor, what happens? I think I've got this explanation here somewhere. Any idea? I think it's in the resistors topic, yes. Yeah. Gets hotter. So here I'm talking about a bulb. In a bulb, you have a filament, which is like basically a piece of metal, which works like a resistor. It will increase. So temperature increases. Yep, well done. Temperature increases. Next question, we've got another calculation using the equation Q equals IT. You don't really get what a resistor is. Okay, a resistor is just a component which, if you've got a circuit, like here, see here, we've got a resistor here. If we've got a circuit, and imagine without this resistor, there could be like a lot of current going through it. There might be 30 amps. And 30 amps might be too much for this LED. It might cause it to break, for example. So what they do is they add a resistor in it, because a resistor provides resistance to the circuit, and it decreases current. So the whole point of it is to decrease current. So now, instead of it being 30 amps, it might be 20 amps. And the 20 amps is basically okay for this LED to be used because it's not too much for it. Does that make sense? So you can have loads of different types of resistors. This is a fixed resistor. But yeah, it's basically used to decrease the current in the circuit. Let me know if that makes sense. Charge flow equals current times time. Okay, good. So now what we can do is just times the two numbers. So 0.02 times by 180 seconds, which gives you... Anyone worked it out yet? No? I think it's 3.6. Put that in the calculator, should give you 3.6. Yeah, well done. In an experiment, a beam of alpha particles was directed at a thin sheet of gold foil. This is basically Rutherford's experiment. Most alpha particles pass straight through the gold foil. Alpha particles which passed close to the nucleus did not pass straight through. What happened to the alpha particles which passed close to the nucleus of the gold atom? Anyone know the answer? It's only one mark. Let me get the notes up on that. So that's the development of the model of the atom, because this is what Rutherford did to when he discovered the nucleus. It's the gold foil experiment. He got alpha particles, he fired gold foil at it. Most of them, nearly all of them, went past straight through. which told him, yep, Harry, well done, which told him that most of the atom is empty space. But then some of them, you can see here, were deflected. That basically told him that there was something in there which was very dense and concentrated in mass, which we know is the nucleus now. So what happened to the alpha particles which passed close through? You can say they were deflected. That's enough for them, Mark. The results suggested that the diameter of the nucleus of a gold atom is 1/6,000 of the diameter of an atom. The diameter of a gold atom is 0.18 nanometers. Calculate the diameter of a gold nucleus in nanometers. They've just given you, they've made this really complicated, but it's actually not that complicated. They've just told you 1/6,000th of the size. So we basically just need to find 1/6,000th of 0.18. Let me know if you do get an answer, guys. You can work it out now. So all you need to do is 0.18 times by 1/6,000, or you can just do divided by 6,000. Both of them will give you the correct answer. And you should get a really small number. So you got to be careful with your zeros here. So let me try it on my calculator here. Yeah, so you should get 0.00003. If your calculator might automatically put it in standard form, you can either write it like that, or you can put it as 3 times 10 to the minus 5. Yep, well, we got it. 3 times 10 to the minus 5. Or you could write it as 0.123 zeros and 3. Either one's fine. Yeah, at least he's got it as well. Well done, guys. Okay, next question. Further experiments show that the gold nuclei are surrounded by electrons in different energy levels. Figure 1 shows 3 of the energy levels around the nucleus of a gold atom. The electron in energy level B, so that's basically, energy level is just another word for the shell, okay? It's in the second shell. It absorbs electromagnetic radiation. Which energy level will the electron be in after it's absorbed electromagnetic radiation? This is one of those topics that people usually forget about. Let me remind you. Anyone know the answer? Let me know in the comments if you know the answer. This will be under atomic structure. C, yep, C is correct. Well done. So this is what happens here. We've got two scenarios. It's in the notes. So here on the left, you can see that electron started off in the lower energy level, but then it absorbs electromagnetic radiation. And that causes it to go up an energy level. It's basically gained energy from that electromagnetic radiation, which has caused it to go up. But then if it was to do the opposite, if it was to emit electromagnetic radiation, it will lose energy and it will go down an energy level. So this question is saying it absorbs. That's the key word. If it says emits, then, Harry, the answer would be A. No, sorry. Yeah, no, Harry, you're right. The answer is not C. Answer is not C. It's A. It goes up. I thought it was numbered the other way. So the answer is A, because it goes up an energy level. So it gets further from the nucleus. So let me repeat that again. If it gains energy, it's going to go to a higher one, which is further away from the middle. And if it loses energy, it goes to a lower one, which is closer to the middle. Hope that made sense. Let me know if that didn't make sense. I can explain it again. Figure 2 shows how the temperature of a small, why does it move out? It's basically, so this is the closer it is, the lower the energy level. So this is the lowest energy level, and this is the highest. lowest to highest. When you're in the middle, you've basically got an energy between the lowest energy and the highest energy, right? So here, this is where the electron's starting in this level. If it's absorbing EM radiation, it's absorbing energy, so it gets more energy, so it goes to the higher one, which is further out. If it emits electromagnetic radiation, it's giving off energy, it's losing energy, so it goes to a lower energy level. So it goes closer to the nucleus. Does that make sense, Will? Nice. Okay. Figure 2 shows how the temperature of a small sample of gold changes as it's heated from a solid to a liquid. What is the melting point of gold? What do you guys think? How do you work out the melting point from that diagram? This is in topic 3. It's all about specific latent heat. This is a heating and cooling graph. So it's basically this graph here. So this is starting off as gold. So starting off as a solid. So can you guys see in the graph here, we've got the solid here. It melts and turns into liquid. So this point here, where it goes flat, every time the graph goes flat, it's changing state. So it's either changing from solid to liquid, liquid to gas, or liquid to gas, or gas to liquid. So it's either melting, freezing, boiling, or condensing whenever it's flat. Here, this is the solid part. This is the liquid part. So that means this is the melting part. So what we need to do is we need to read off the graph here. We've got to read off what that is. What number is that, do you think? Again, it's a bit awkward, these numbers. So we've got 10 squares. 10 squares represents 250. So that means 1 square would represent 25. So 10 squares is 250 because it goes from 1,000 to 1,250. So that means 1 square is 25. How many squares are there here? 1, 2, 3, 4. So 4 times 25, that makes that 100. So it's basically 1,000 plus 100, which is 1,100. Be careful with these reading graphs. They make it really awkward. You've got to look at the scale properly. 1,100 degrees C. Good, a few of you got that. How many minutes did it take for all the gold in the sample to change from solid to liquid? What would you say the answer to that is? So remember, this first line is for a solid. The second line is when it's turned into a liquid. So basically from here to here is the time it takes for it to melt. So you got to read it off. 4 and 12. So it goes from 4 to 12. So that means it is, yep, well done, 8 minutes. Because it goes from 4 to 12 minutes. Cool. What does the gradient of the graph in figure 2 represent? So when you get a question like that, gradient, remember gradient is the change in y over the change in x. So look at what the y-axis is. The y-axis is temperature. X-axis is time. So it's temperature over time. What does that mean? That basically means whenever something's over time, it means it's the rate. So this is the rate of change in temperature. So time means rate. If anything's divided by time, it means it's the rate. And because it's temperature over time, it means it's the rate of change in temperature. Next question. A hybrid car has an electric motor and a petrol engine. petrol is non-renewable. What is meant by non-renewable? What do you guys think? Let me get this topic up. Energy resources. What does non-renewable mean? Here we go. So these are resources that will eventually run out. An energy resource that will run out. Yeah, Harry. Finite resource that cannot be replaced. That's fine as well. Okay, here we got a calculation. They haven't given us the equation, so you need to look this up in the equation sheet. We have electric motor. To charge the battery, the car is plugged into a main supply at 230 volts. It uses 6.9 kilowatts. So what's this? This is power. This is potential difference. Calculate the current. So we want an equation with P, V, and I in it. You can look that up into the in the equation sheet, and you'll get the equation. P is equal to IV. Power equals to current times potential difference. We want to rearrange this equation to get current as the subject. So that's going to be power divided by potential difference. So that's because, let me show you the triangle. So the triangle we're dealing with is P at the top, I, and V at the bottom. So I would be, if you corrupt the I, you get P over V. P is 6.9 kilowatts. You need to convert that into watts. There's a conversion there. So 6.9, you need to times that by 1,000 to give you the answer in watts. Then you can divide it by the 230. Anyone got an answer yet? So that's going to be 6,900 divided by 230. You got 30. Yep, well done. 30 is the answer. 30 amps. So if you've got 4 marks, it usually means there's some sort of conversion or units you have to give, or extra significant figures. There's something extra to the calculation. It's not just subbing in the values. You don't just put 6.9 and 230 into the equation just like that. Usually there's something else to do. So look out for that. Look out for the marks. Well done, guys. Mains electricity is AC. Explain the difference between AC and DC, direct and alternating potential difference. What would you guys say for that? For 2 marks. For 2 marks, you just need to say what AC is and what DC is. That's enough for 2 marks. Let me know what you think. Here we go. Direct current flows in one direction. Yep, thank you. And alternating current is in the opposite direction. Good. That's enough for both marks. Alternating current changes direction. The cable used to connect the car to the main electricity supply has a low resistance. Explain why it's better to use a cable with a low resistance than to use a cable with a high resistance. So remember what we said. So I think this is what you asked, Lucy. What's the whole point of a resistor? It's not asking about a resistor. It's just asking about resistance. Resistance is something that decreases the current in a supply. So you want this to charge a car. It's better to use low resistance because low resistance means higher current. So remember, resistance affects current. So if you have low resistance, you're going to have high current. Whereas if you have high resistance, you're going to have lower current. So it's going to take longer to charge the car. This whole thing is used to charge a car, isn't it? So you can say lower resistance means there is a higher current. So it's faster to charge the battery. Charge. Okay, next question. So this one's about atomic structure and radioactivity. So we've got a radioactive isotope. The nucleus emits gamma radiation. Gamma radiation, let me get you all the different types of radiation you can have. Remember, you can have alpha, beta, and gamma. The differences are here. Alpha, beta, gamma. So we'll summarize in this table. What happens to the mass number and the charge of a nucleus when gamma radiation is emitted? What do you guys think? I'll show you here in the nuclear equations. Gamma radiation, the starting and final nucleus are always identical. The reason why is, well done, Georgie. It's because it's 0, 0. Gamma is 0 and 0. So that means the mass number doesn't change and the charge doesn't change. So the answer stays the same, stays the same. Next question. Why is it difficult to detect gamma radiation? This is a tricky one, but it's to do with that table I showed you earlier. It's all about ionizing power. All of them are ionizing, but the highest one, the one that's the most ionizing, is alpha. Gamma is the least ionizing. Ionizing basically means it knocks off electrons from the atoms and turns them into ions. Alpha is very good at knocking off electrons. Gamma is not. When you're detecting radiation, you use something called a Geiger-Müller tube or Geiger counter. For you to detect radiation, you're basically counting on the atoms to ionize. So gamma, because it has a low ionizing power, it's less likely to ionize the atoms inside the Geiger counter, so it's harder to detect. All you need to say is it's less ionizing, and you'll get the mark. It's less ionizing. Or what else you can say? Because the penetrating power is very high, you could also say it might pass through the detector. Because remember, to stop gamma, you need thick lead or concrete. So it might actually just go straight through the detector. So you won't be able to detect it. So two answers there you could give. Either one's fine. Next question. Activity is the rate at which a radioactive source decays. A teacher measured the count rate from a sample using a Geiger-Müller tube. Explain why the count rate was less than the activity of the sample. This is another tricky one. So activity is basically how often it decays. Okay, so imagine you've got a sample. You've got a sample that's radioactive. Okay, so this is like a block of uranium or something. This starts to radiate. Okay, so let's say it gives off gamma rays. But the thing is, it doesn't give gamma rays off in one direction. It gives it off in many directions. Okay. How a Geiger-Müller tube works is you basically point it. So this Geiger-Müller tube, what you do is you point it at whatever it is you're measuring. Okay, so this is the Geiger-Müller tube. You point it, the radiation goes into the Geiger-Müller tube, and every time it senses something radioactive, it clicks, it gives a reading. It doesn't give you the activity because you're only detecting the rays that are going in this direction. Look at all the other rays. You've got these rays coming out. You're not detecting any of these. So because you're only detecting the ones that are directly hitting the GM tube, the Geiger-Müller tube, it's always going to be lower. So how do you get 2 marks here? What you can say is the radiation spreads out in all directions. That's 1 mark. Only some of it passes into the GM tube. Hope that makes sense. Again, let me know if that doesn't make sense. I'll explain it again. Let's see how much we got left. Okay, we're doing good for time. Okay. The teacher investigated how the thickness of lead affected the amount of gamma radiation that could pass through it. Explain why the teacher stood as far away as possible from the apparatus. What do you guys think? You're dealing with this. This is radioactive. So the teacher is investigating it. So they're carrying out the experiment. They had to stay as far away as possible from it because they want to basically reduce the amount of radiation that hits them because, yeah, so that they're not exposed to it. Because, so that's all 1 mark. What's the second mark for? So you can say to reduce the amount of radiation. 1 mark. What's the second mark for? No, it's because it's the dangers of radiation. Because it increases this. It increases the chance of you getting cancer or getting mutation. Because radiation increases the chance of cancer. Increases the chance of cancer. Okay, good. Next up, we've got the teacher concluded that the count rate was not inversely proportional to the thickness. Okay, so let's look at this table here. We've got the thickness of lead. So remember the experiment. We've got this thing, which is radioactive. We've got the GM tube, which is basically taking readings of the radiation it receives. And then you're increasing the thickness. So it starts off thin, and then we're increasing the thickness of it. And obviously, as you increase the thickness, less radiation is going to pass through, which means the reading is going to go down. So if the reading goes down, does that always mean it's inversely proportional? What does inversely proportional mean? Inversely proportional basically means if you double one, the other halves. If you double one, the other halves. Directly proportional means if you double one, the other doubles. So you basically need to prove that it doesn't do that because it's not inversely proportional. So you can use some of these numbers. So let's use some that double. We've got 0.5 going to 1 here. That's doubling. So that means from here to here, it should half, because that's what inversely proportional means. Does it half? No, it doesn't, because half of 110 should be 55. So use the data in the table above. So how would you show this in your exams? Just add the number and just say from 0.5 to 1, the thickness doubles. But the count rate should be 110 divided by 2, which is 55. But it is not. So you've got to show some calculations here. Let me show you another example. We've got 1 going to 2 here. As you go from 1 to 2, you're doubling the thickness. Does the count rate half? No, because 60 halved times by half or divided by 2 should give you 30, but it gives you 18 instead. So that's not going to get you the mark for that either. All of that should give you all the marks for that question. Okay, hope that makes sense. Let me know if there are any questions. Okay. Okay, on to the next one. We've got a nuclear equation here. Complete the equation showing the decay. So we've got this, an electron. Which type of radiation is this? Does anyone know? We've got this here. Let's look at nuclear equations. So alpha decay, you can either write it like this, or in some equations, it'll come up as a He because it's a helium nucleus as well. Beta decay, you can either write with a beta symbol or an electron. That's what we've got here. We've got an electron. That E represents an electron because a beta particle is essentially an electron. So you can put the numbers that we've got up there. So that's 0 and -1. And then you can kind of work out what these numbers would be. Can you guys figure it out? What number should be up here? So basically 140 is equal to 0 plus something. And the bottom one, for the bottom ones, it's 57 is equal to -1 plus something. So top one, yep. Top one stays as 140. So you can just write 140 there. And bottom one is going to be 58. Well done, guys. So 140 and 58 is the answer for those. All right, nearly done. Nearly done. There are other isotopes of cerium which are radioactive. Different isotopes of cerium have different half-lives. Half-life of an isotope can be found by studying how the number of atoms change over time. Figure 2 shows how the number of atoms in a 120 gram sample changes over time. Okay. So we've got the number of atoms here. And we've got the number of atoms changing, decreasing. Determine the ratio of the number of cerium atoms in the sample when it was 100 seconds old compared to when it was 350 seconds old. Okay, so whenever you get, it's confusing. The question actually sounds very complicated, but whenever you get a graph like this for radioactivity, it almost always, I think always, 90% of the time means it's a half-life question. Okay, so don't get thrown off. Have they even mentioned half-life here? No, they haven't. So they're trying to throw you off here, but it's a half-life question. So here, we've got it in the notes here. Half-life is the time it takes for the number of undecayed nuclei, so basically the number on the y-axis, to half. So the time it takes for it to half. So I've got example here with the graphs. So whenever you get a graph like this is what you got to do. You got to look at whatever the initial value is, go to half of it, get a ruler, go across, get a ruler, go down. Okay, so let's look at R1. We've got 5 here. We need to go to half of 5, which is 2.5. 2.5 is here. We need to go across. And then we need to go down. And that's going to give you the half-life. So the half-life is 50 seconds. So that means every 50 seconds, the number halves. So half-life is 50 seconds. Yeah, well done. That is, how many marks does that give you? That only gives you, that only gives you 1 mark. The question's asking, determine the ratio from when it was 100 seconds old compared to when it was 350 seconds old. So to work out how many cerium atoms there were when it was 350 seconds old, you need to work out how many half-lives there are in 350 seconds. So 1 half-life is 50 seconds. How many half-lives is in 350 seconds? And how many half-lives are there in 100 seconds? Because it's asking to compare 100 seconds with 350 seconds. So those are 3 things I want you guys to tell me. How many half-lives are there in 100 seconds? 2 things. And how many half-lives are there in 350 seconds? Yep, 2 half-lives here. 2 half-lives in 100 seconds. 7 half-lives in 350 seconds. So that means between here and here, how many times has it halved? So between 100 seconds and 350 seconds, how many times has this sample halved? Any ideas? Yeah, Will, well done. 5 times. So it's halved 5 times. So that means you just need to do half times half times half times half times half. So half to the power of 5. Half to the power of 5 will give you the final answer. Because what you've done is you've taken your initial reading, 2 half-lives, and you've halved it 5 times. Anyone know what that is? Let me know what you get. So let me explain again what we've done while people are working that out, because this is a confusing one. First thing we did was work out the half-life. So remember what half-life is. Half-life is the time taken for the number of atoms to half. Okay. At the start, we had 5 times 10 to the 23 atoms. To find the half-life, we went down to 2.5 and we worked out what the time was for it to half. That was 50 seconds. The question wasn't asking what the half-life was. It wanted us to work out how much it was at 100 seconds, how much it was at 350 seconds, and compare the ratio. So what you need to do here is, because we know 1 half-life is 50 seconds, we also know 2 half-lives is 100 seconds, because every 50 seconds, there's another half-life. That means 350 seconds, there's 7 half-lives. So by the time you've gotten to 350 seconds, this initial value has halved 7 times. But the question's not asking how many, the ratio between the initial and the final. It's asking, it's being very awkward, this question. It's asking the ratio between this and this, 100 seconds to 350 seconds. So you need to work out how many times it's halved. So how many 50s are there between 100 and 350 is 5, because the difference between the two is 250 seconds. So there's 5 50s, which means there are 5 half-lives. So you do half to the power of 5, which is, looking at the answers, yes, everyone's getting it. It's going to be 1/32. That is a tricky question, I must admit. So you can either write like that, or you can write 1/32. 1/32. Either one's fine. You can leave it as a fraction as well. Okay, well done, guys. Last question. How much time do I have? Oh God, got 8 minutes. Okay, remember, guys, it cuts off automatically after 2 hours. So hopefully I can get this done before then. Determine the activity of the sample when the sample was 20 seconds old. Activity of the sample. So we've got the number of atoms. What we need to find here is the gradient, because activity is basically the rate, the speed at which these atoms decay. So we need to find the gradient. It's going to be quite hard for me to draw the gradient with the iPad, but let me try. So we want to find out the activity at 20 seconds. So let's mark where 20 seconds is on the graph. It's around here. So you want to draw a tangent at 20 seconds. So let me see. So whenever you draw a tangent, you want to make sure that the line that you draw is the same gradient as that single point. So I'm going to try and draw this tangent here. If it works, does it work? No, it's not working. Okay, tried my best. Let me try one more time. If not, I'm just going to draw a rough one and I'll tell you what to do. Yeah, not working. So let me draw a rough one. So you got to make it go through that point. Get a ruler, make it go through that point. It's not going through the point. Getting there, closer, nearly there. How much time do I have? close enough. Okay, so we got a line here. We want to find the gradient of that line. So what you need to do is find the change in y over change in x. So we got this reading here. Then let's pick a nice number to do that with. Let's pick this 2 here. So I'm going to draw a triangle here. 5 minutes. So 1, 2, 2 point. So what's this height here? You're going from 2, you're going 1, 2, 2 point. I'd say that's about 2.8. So the height here is 2.8. Don't forget it's times 10 to the 23. And then we want to find the time. So that's basically the width of this triangle. So that's from this reading here. Let me use a different color for that. So we want to take this reading. So that's going from 0 to, I'd say that's around, so that's 50, 52, 54, 56. So I'd say this is 56. So 2.8, remember this is times 10 to the 23 divided by 56. What does that give? Yeah, roughly 2.8 times 10 to the 23 divided by 56 gives roughly 5 times 10 to the 21. I want everyone to try that out yourselves, yeah? So try and draw a tangent. Remember, a tangent should just touch that single point, and it should have a very similar gradient. It needs to have it has as close as possible to the gradient of that point. So mine, yeah, mine's pretty good. Yeah, that's pretty good. You just need to then draw a triangle, find out the change in y over change in x. Your numbers are going to be different to mine, but just show you're working out to get the marks. Change in y over change in x. So always draw the triangle to show the examiner that you've actually tried the question and you know what to do. Even if you make a mistake here, at least they can give you like working out marks. So you do that and you get your answer 5 times 10 to the 21.